This is the video for section 13.4. In this video, I'll be working examples 2 and 3. So when you get ready to work those problems, we'll do that together. Example 2, graph the function f of x equals x plus 1 over x. Keep in mind, we don't want just the sketch of a graph. We want a lot of details. Where is the function increasing and decreasing? Where is it concave up, concave down? So again, we want very specific details to construct an accurate graph. The first thing that we're going to do is find the domain of this function. Excuse me. Notice the domain is going to occur where our function is defined. It's not going to be defined if we get a 0 in the denominator. So we need to exclude 0 from the denominator, from the domain. So we have negative infinity to 0, union 0 to infinity. So we're going to have a graph on the left side of x equals 0 and on the right side of x equals 0. I can expect my graph to come in two branches. The next thing that's helpful is to find the x-intercept. When we find the x-intercept, we set y equal to 0. So we need to solve the equation 0 equals x plus 1 over x. Now, an easy way to solve this equation algebraically is to multiply both sides by that common denominator that I see over there on the right side, which is x. Multiplying the left side by x gives us a 0. And when we distribute x over here on the right side, we end up with x squared plus 1. Now notice, this is not factorable, so I'm not going to be able to get real roots. If you want to see this more specifically, think about what would happen if I subtract 1 from both sides, and then I try to take the square root of both sides. If I attempt to take the square root of both sides, considering positive and negative versions of the square root, I would end up with x equals plus or minus I. I is the symbol for the square root of negative 1. It's an imaginary number. So what that tells us is simply that this function has no x-intercepts. So if you obtain something strange like that, like an imaginary solution to your equation, it simply means the graph is not going to cross the x-axis. You could verify this easily with your graphing calculator. Next, we want to locate the vertical asymptote. The vertical asymptote is going to occur where a denominator is equal to 0. And we've already observed x equals 0 makes that fraction 1 over x have a 0 in the denominator. So the equation of our vertical asymptote is x equals 0. So notice we left this value out of the domain. We're skipping over that. But in our graph, we will see an actual boundary line there, a vertical asymptote at x equals 0. So no x-intercepts, 2 branches, and a vertical asymptote. The next thing we want to do is investigate symmetry. Every single time we investigate symmetry, we begin by finding f of negative x. So I'm thinking about my original function, which was x plus 1 over x, and I'm going to replace the original x's with negative x's. And then I'm going to simplify. We could clean that up a little bit and call it negative x minus 1 over x. Notice this is the exact opposite of the original function. The original function had 2 positive terms. F of negative x has 2 negative terms. So every term changed sign. From the description on page 1, you can recognize that this is called an odd function, or it has symmetry about the origin. So this has kind of a radial symmetry, symmetry about the origin. So remember, this graph is going to have 2 branches. We know that because the domain comes in 2 intervals, and we can expect both of those branches to be symmetric or reflections of each other if we rotate them about the origin. Next, we're ready for a little bit of calculus. It says find the critical numbers and construct a sign chart to determine where the function is increasing and decreasing. Identify relative extrema. So to find a critical number, I need the first derivative. Now remember, the function was x plus 1 over x. The derivative of x is 1, and the derivative of 1 over x is negative 1 over x squared. Now, in case I lost you there, remember, you can think of 1 over x as x to the negative 1 power. right? So x plus 1 over x can also be written x plus x to the negative 1. So the derivative of that first term is 1. If I apply the power rule to the second term, I have negative 1x to the negative 2, which can be rewritten in fraction form like that. So either way you want to write it is fine. To find a critical value, we set our first derivative equal to 0, and we solve that equation for x. Now in this case, I'm just going to add 1 over x squared to both sides. And then we can multiply both sides very easily by the common denominator x squared. Now you could have done that on the previous step, kind of like we did when we were looking for the x-intercept. Either way is going to work out great. So we end up with 1 equals x squared. Now I can take the positive and negative square root of both sides. I'm going to come up with my critical values. My critical values are apparently x equals negative 1 and positive 1. However, there's another one that we have overlooked. Did you overlook it? This one's easy to forget about. Remember, in the definition of critical numbers, they occur either where your derivative is equal to 0 or where your derivative is undefined. Well, if I look at my derivative, it's going to be undefined if x is equal to 0. So don't forget to check that one. I've left that out a bunch of times. It's very easy to forget. So I have 3 critical values. Now, we're going to construct a sign chart to figure out where the function's an increasing function and a decreasing function, and that helps us to identify the maximums and the minimums. So I'm going to put these numbers on a sign graph. I'm going to divide it up into intervals according to the numerical order of those critical values. I'm going to write my derivative over here to keep that in mind so I can think about it. Then remember, we choose test points from each interval. So I'm going to choose a test point less than negative 1. Let's use negative 10. Anything less than negative 1 would work. If I plug 10 in for x, I end up evaluating 1 minus 1/100th. Well, that's going to be a positive value. Remember, you're not necessarily interested in the value, you're just interested in sign. So I know it's going to be positive on that interval. Now we can choose a test point between 0 and negative 1. How about we use negative 1/2? Well, if I plug negative 1/2 in for x and I evaluate it, I'm going to see the result is negative. You can calculate that, or you can type it into your calculator to understand. But again, to be clear that you know what I'm doing, I'm taking my test point negative 1/2, I'm plugging it in for x, evaluating the derivative to see the sign of the result. If we do the same thing with test point 1/2, we would observe the derivative is negative. And if I take test point like 10 and plug it into the derivative, we would see that it is positive. So we have an increasing function, and then a decreasing function, and then something strange happens at 0. Now remember, that was our vertical asymptote. This side is decreasing and then increasing. Okay? So it appears that we're going to have a relative maximum at x equals negative 1 and a relative minimum at x equals 1. Now let's just kind of keep a tally of this information. Our function is going to be increasing where the derivative is positive. So it will increase from negative infinity to negative 1 and then 1 to infinity. So we're looking at this interval and this interval. The function will be decreasing where the derivative is negative. We can see that derivative is negative here and here. So reading those critical values left to right, negative 1 to 0 and 0 to 1. Now you might think, why don't I just call that negative 1 to 1? Remember, we have to leave out x equals 0 because there's a vertical asymptote there. Okay? We have a relative maximum occurring when x is equal to negative 1. Well, when x is equal to negative 1, we need the corresponding y value, so I can plot it on my graph. Now be careful, to get the corresponding y value, we've got to go all the way back to the original function, and I'm going to calculate f of negative 1. That's negative 1 plus 1 over negative 1, or how about we call that negative 1 minus 1 looks like negative 2. So the ordered pair location for my relative maximum is negative 1, negative 2. Now, be careful. These are intervals. Those are x values left to right. On my relative extreme values, these are going to be ordered pairs. X, Y ordered pairs. So the notation looks the same, but these are intervals left to right. These are ordered pairs X, Y. Okay, we've got one more to identify here. It's our relative minimum or our local minimum. Either way you want to say it is correct. It occurs when X is equal to 1. And if I take 1 and I plug it back into my original function, see if I can get my screen to scroll. If I plug in X equals 1, we'd have 1 plus 1 over 1. Easily we would obtain relative minimum 1, 2. That's a lot of good information for our graph. We could sketch a pretty decent graph using that information. But we not only want to know where is it increasing, decreasing, where are the maximums and minimums, but we want to know how does it bend as it's increasing and decreasing. And that's what we're going to use our second derivative for. Now everything that we're going to do with the second derivative is going to feel like what we just did with the first derivative. It's only the conclusions that are going to be different. So to work on this one, we need to find our second derivative. Looking at my first derivative, the first term was 1. The derivative of 1 is 0. So that first term is going to go away. And we can think about this term as negative x to the negative 2, right? So when I differentiate it, using the power rule, I would get 2x to the negative 3. Or I could write that 2 over x cubed. Now, we're going to set that second derivative equal to 0, just like we did with the first derivative, and attempt to obtain what's the parallel of our old critical numbers. We want to know where is that second derivative equal to 0. Well, this one is clearly never equal to 0, but it is undefined where x is equal to 0, because that gives me a 0 in the denominator. So that's not a critical value. We're going to call that a potential inflection point. But just like we did previously, I'm going to put this potential inflection point on a sine graph. And I want to judge the sign of my second derivative on each interval using test points. So I could pick a test point less than 0, such as negative 1, and I would see that the sign of my second derivative is negative. If I choose a test point greater than 0, such as 1, I would see my second derivative is positive. So a negative second derivative indicates that the function is concave down, and a positive second derivative indicates that the function is concave up. Now remember, we're using a sine graph. It looks a lot like what we did before, but on the first derivative, remember a positive first derivative means the function is increasing, a negative second derivative means it's decreasing, so on and so forth, okay? So the derivative, first derivative tells me increasing and decreasing. The second derivative tells me concave up or concave down. So we could make our conclusion. The graph is going to be concave up. You can think of it as holding a cup in the upward direction. That describes how the curve bends. It's going to be concave up from 0 to infinity. And it's going to be concave down. Think cup down. If you hold a cup with its opening down, that's the shape of the curve. This occurs between negative infinity and 0. So we could say it's going to be concave up on the right side of the asymptote, and it's going to be concave down on the left side of the asymptote. Okay? That's a lot of information. Let's try and organize it using this table. Now we're going to break our number line up into 4 different intervals as described on row 1 of our chart. We want to look at the sign of the first derivative and the second derivative on each interval, and we're going to try to put that information together to figure out what the graph looks like. So from negative infinity to negative 1, looking at our first derivative, from negative infinity to negative 1, the sign of the derivative was positive. That means the curve is increasing. From negative 1 to 0, looking at our first sign chart, the sign of the derivative we discovered was negative. That means the function is decreasing. From 0 to 1, again, the sign was negative. Our function is decreasing. And from 1 to infinity, the sign was positive, so the function is increasing. Okay? Now, let's look at our second sign graph, where we were examining f double prime, the second derivative. From negative infinity to negative 1, and then again from negative 1 to 0, all this stuff, the sign of our second derivative was negative. This means the shape of the graph is concave down. From 0 to 1 and 1 to infinity, that's this side. The sign of our second derivative was positive. That means the curve is concave up. So we've got a good variety of combinations to discover here. So let's put this together and figure out the shape of the graph. Well, a curve that is increasing and concave down, now it's going to be going up, but it's going to be the shape of a cup down. It's going to look something like this. Okay? A curve that is decreasing, it's still concave down, so I'm still thinking cup down, but now it's decreasing. It's going to go something like that. That's the shape of the curve. Now, a function that is decreasing or going down, but is in the shape of a cup up, is going to look something like this. Okay, and then increasing, concave up, will look something like this. All right, that's a whole lot of information. Let's see if we can transfer this to a graph. So important points on our graph will be relative extreme values, critical numbers, asymptotes, that sort of thing. We know that right smack dab in the middle of our graph, we have a vertical asymptote at x equals 0. I'm going to get that out of the way first. That's going to serve to be the boundary line of our graph. Now, we did some work up here. We found two important points. We found the relative maximum and the relative minimum. Let's go ahead and put those on the graph. -1, -2, and 1, 2. Now, as we graph these, think about the relationship between these 2 points. One of the first things that we did was look at symmetry of the graph. We said the graph should be symmetric about the origin. Well, this point, 1, 2, if I reflect it around to the other side of the origin, would have mirror image -1, -2. Now, isn't it interesting? This one we said was going to be the maximum, and this one is going to be the minimum. Now you're thinking, that can't be right. How can a maximum be lower than a minimum? Well, it's going to be valid on this graph because I'm looking at this graph in two different pieces. Now, to help us put all this information together, if you haven't done so already, let's take a peek at the graphing calculator. I'm going to go to y equals, I'm going to type in the original function, x plus 1 over x, and then I'm going to do zoom 6 to begin taking a look at this graph in the standard viewing window. Okay, so notice we have increasing concave down, then we have decreasing concave down. On the other side, we have decreasing cup up, concave up, increasing concave up. Okay, so all of that lines up with the information that we discovered in our table. So let's sketch our graph. Increasing concave down, decreasing concave down. Now remember, the graph is going to follow that vertical asymptote on its way out. Decreasing concave up, increasing concave up. I think I can do a better job of this branch. Let me do that one more time. Something like this, and then heading towards that vertical asymptote. Okay, so we have our maximum, our minimum. We did not get inflection points because we had a vertical asymptote right there in the middle. But do notice we have a very detailed sketch of the graph. Okay, that was so much fun. I know you can't wait to do it again. So let's go ahead and work through example 3. Many of the details will be familiar. What I want you to think about is we're making these sign graphs. We're making one for the first derivative. That tells me increasing, decreasing, and relative maximum and minimum. And then we make a sign graph for the second derivative. That's going to tell me concave up, concave down, and inflection points. So let's try this one. Graph the function f of x equals 3x squared over x squared plus 5. The first thing we need to do is find the domain. For the domain, we're going to need to exclude values for which the denominator is equal to 0. Now, in this case, the denominator is never equal to 0. No matter if I plug a positive or a negative number in for x, or even 0, when I square that number and add 5, it's always going to give me a positive number. So the denominator is never equal to 0. That means the domain of this function is negative infinity to infinity. Next, let's find the x and y intercept. Well, if I want to find the x-intercept, I'm going to set y equal to 0. So we need to solve 0 equals 3x squared over x squared plus 5. If I multiply both sides by the denominator in order to cancel it, I get a much easier to work with equation. We end up with 0 equals 3x squared, because everything over here on the right side cancels. Now, if I divide 0 by 3, and then I take the square root of both sides, I'm going to end up with one solution there, x equals 0. So remember, we set y equal to 0, we found x equal to 0, so our x-intercept is 0, 0. Now, we're going to go ahead and go through this, but if I find the y-intercept, we're going to get something familiar, okay? The plan for the y-intercept is to set x equal to 0. So looking at the original, I'm just plugging 0 in for x. If I evaluate that, I would end up with 0 over 5, which is equal to 0. So my x-intercept and my y-intercept produce the same point. Okay, so the x and the y-intercept, both of those points are in a single location at the origin. Next, let's locate the horizontal asymptote. In this case, we're not looking for a vertical asymptote because the denominator is never 0. Now, to find the horizontal asymptote, we'll have to remember what we learned in our first chapter. We need to find the limit as x approaches infinity of the function 3x squared over x squared plus 5. Now, this may be painful to remember, but it's good to review this because we'll see it again on our final exam. Now remember, if the degree of the numerator and the denominator are equal, as they are in this case, then the limit is the ratio of leading coefficients. Leading coefficient on the top is 3, leading coefficient on the bottom is 1, so the limit here is equal to 3. Thus my horizontal asymptote is equation y equals 3. You may want to go back and review those 3 rules when you're calculating a limit at infinity. Next, let's investigate symmetry. To investigate symmetry, I'm always going to start with f of negative x. So I'm going to replace all the x's in the original function with negative x's, and then simplify. In each of these cases, when we square a negative, it gives us a positive. So I can simplify. And I notice that the result is the same as the original function. This tells me that the graph is symmetric about the y-axis. Okay, so if every term changes sign, like it did in example 2, it's going to be symmetric about the origin. It's going to have that rotational symmetry. If we come back up here and look, if I take this piece and I rotate it about the origin, it's going to land right there, okay? If you evaluate f of negative x and nothing changes sign, everything stays the same, it's going to be symmetric about the y-axis. So I should see a mirror image on the left and right side of my y-axis. That'll help me with critical numbers, inflection points, all that good stuff. Now we're ready for our sign graphs. To find the critical numbers, we're going to need the first derivative. To find the first derivative of this function, hopefully you can recognize this, we're going to need the quotient rule. I know that's your favorite derivative rule, right? Of course, this is the longest rule. So we're going to start by squaring the denominator, then we lead with that term in the numerator, multiply by the derivative of the numerator, minus derivative of the denominator times the numerator. So we're getting lots of practice with our derivatives here. Now, let's simplify. We'd end up with 6x cubed plus 30x when we distribute, minus, that's going to give me a negative 6x cubed all over our denominator squared. So this one cleans up nicely. The derivative then is 30x over x squared plus 5 quantity squared. Now we want to set our derivative equal to 0. When I set it equal to 0, I have to consider where is the numerator equal to 0 and where is the denominator equal to 0. Where the numerator is equal to 0, I get a critical value. Clearly, that occurs at x equals 0. Where the denominator is equal to 0, the derivative is undefined, but that is also classified as a critical number. But notice, if I set that denominator equal to 0 and I solve for x, I'm going to get another imaginary number. So it looks like we only have one critical point, x equals 0. So we want to put this number on our sign graph and look at what happens on either side of our critical number, x equal to 0. Now, if I consider my derivative, notice, because the denominator is squared, it's always positive. So it's not going to change the sign of the derivative. So the only factor I need to consider is the sign of 30x. If I choose a test point on the left of 0, I would discover my derivative is negative. And if I choose a test point on the right of 0, I would discover that the derivative is positive. So remember, a negative first derivative means the function is decreasing. A positive first derivative means the function is increasing. So it appears we have a relative minimum when x is equal to 0. So we're going from decreasing to increasing. Right there in the middle, we have a relative minimum. So our function is going to be decreasing from left to right. Leftmost x value is negative infinity. Rightmost x value on this interval here is the critical value 0. Then it's going to be increasing from x equals 0 to infinity. And finally, we have a relative minimum or a local minimum when x is equal to 0. To find the corresponding y value, we plug that back into the original function. But hopefully you remember from our intercepts, when x is 0, y is equal to 0. Okay, that's good information to begin our graph. Now let's look at the detail about the shape of the graph. We know where it's going up and down. Let's see if we can figure out how it bends along the way. So next thing that we need to do is analyze our second derivative. So looking at this for the expression of our first derivative, to find our second derivative, we're going to need to apply the quotient rule again. We know the quotient rule begins by squaring the denominator, and then we lead with that term in the numerator and multiply by the derivative of the numerator, minus the derivative of the denominator. Now, are you ready for the chain rule? We have a function of x raised to a power there in the denominator. So I'm going to start with the power rule. Looking at the denominator, the exponent is 2, so I'm going to bring that down in front. Keep the base the same. Decrease the exponent by 1, and then I'm going to multiply by one more thing. Do you know what it is? Derivative of that base there is 2x. Okay, so that completes the derivative of the denominator. Completing the quotient rule, now we multiply by the numerator. Okay, let's see if we can simplify this. And we want to simplify it in a convenient way where we don't have to do too much multiplying. So I'm going to look at the two terms separated by that big minus in the middle. And I notice the first term has both an x squared plus 5 and a 30. The second term has both an x squared plus 5 and a 30. So we have a greatest common factor of 30 times the quantity x squared plus 5. Okay, so there's my GCF. Now I'm going to open up a set of brackets and anticipate two terms. We're going to figure out the GCF times what term produces each of those two original terms. So noticing the first term, I have x plus 5 quantity squared. My GCF only has x squared plus 5 to the power of 1, so I need to multiply by another factor there. 30 times x squared plus 5 times another x squared plus 5 gives me that first term. Okay? So really I'm just seeing what's missing from my GCF that's present in the original term. So let's look at our second term. It's kind of long. We're going to need a 2 We already have the x squared plus 5 in our GCF. We're going to need another 2 and an x. We've already got the 30, but we need another x. Okay? We can always check by redistributing our GCF there. So let's do that. 30 times the quantity x squared plus 5 times another factor x squared plus 5 gives me the correct first term. Let's check the second one. This red GCF times the second term. I'm going to have a pair of 2's, an x squared, a 30, and an x squared plus 5. That gives me all the details of that second term. So it's correctly factored. Okay? Let's simplify. If we look at what's inside parentheses here, or inside brackets, we're going to have x squared. And then out here, notice we have minus 4x squared. X squared minus 4x squared gives me negative 3x squared. And then I still have that plus 5 unaccounted for in the numerator. That was a good move, factoring out that GCF, because notice now I'm going to be able to reduce one of these factors. And finally, we have our second derivative, which is f double prime of x equals 30 times. I'm going to try and write this in a more readable way by switching those two terms around. That way I'll have less signs to read, makes it a little more readable. If you like it in descending order, that's absolutely correct. You can certainly leave it that way. Now, this was the whole problem in the first half of the class, right? Find the second derivative. Now we have to make sure we get the derivative right, because our next step is to set it equal to 0 and solve for x. Now remember, I can multiply both sides by this denominator. We've done that several times. When we do, it cancels on the right and zeroes out on the left. Let's go ahead and divide both sides by 30. And we have the equation 0 equals 5 minus 3x squared. Add 3x squared to both sides. Divide both sides by 3. And take the positive and negative square root of both sides. Now, if that was too fast, pause the video as we're going through the steps, work them one by one, and make sure you understand each little algebraic step. Okay, so I have two critical values, plus and minus square root of 5/3. That's not a very convenient number to work with, so I'm going to come to my calculator and approximate it. So the square root of 5/3 is approximately 1.29. Okay, so our critical values are approximately equal to plus or minus 1.29. So let's put those on a number line. If you're out of room, feel free to put a sticky note in here or work on the back side of your notes. No problem doing that. We need to figure out the sign of our second derivative. So I'm just going to put f double prime of x over here. That's what I'm testing. So let's choose a test value less than negative 1.29. Let's try something easy like negative 2. Okay? Now, notice in the denominator, when I plug a negative 2 in right here and square it, it's always going to come out positive. If I add 5 and cube it, that denominator is always going to be positive. So I'm not really going to pay attention to that. Also, the factor 30 is always positive. So the only factor that's important in judging the sign of my second derivative is this 5 minus 3x squared. Again, plugging negative 2 in for x, negative 2 squared is 4. We have 5 minus 3 times 4, or 5 minus 12. Whatever that number happens to be, we can observe it is negative. Remember, we're working with our second derivative. That means the graph is concave down on this interval. An easy test point to use between our negative 1.29 and positive 1.29 is 0. If I plug that into the second derivative, we'll discover it's positive. So here in the middle, it's concave up. On the right side, I could choose the test point 2 and plug that into my second derivative. I would also discover that it is negative. Notice this graph is symmetric about the y-axis, or about x equals 0. I can see that both with my first derivative and my second derivative. Okay, are you ready to compile the information? Let's put it all on this chart so we can kind of sort out what the graph should look like. Now, we discovered that on the left half of our graph, from negative infinity to 0, our first derivative was negative. So it's going to be negative on those two intervals. And we've already observed that means the graph is decreasing there. Also from our first sine graph, we discovered the first derivative was positive from 0 to infinity. So the graph is increasing. Looking at our second derivative, the sine graph we just discovered, we discovered it was negative between negative infinity to negative 1.29. Splitting it here in the middle to compare it to our increasing and decreasing, from negative 1.29 to 0, it was positive. And then on the other side there, also positive. And then finally, 1.29 to infinity, it is negative. Just transferring that information here. If your second derivative is negative, the shape of your graph is concave down. A positive second derivative means the shape of your graph is concave up. And then again, concave down. So this is a great way to compare increasing, decreasing to the shape of the graph. If a function is decreasing and concave down, it's going to look something like this. Decreasing concave up, I'm still decreasing, but I'm holding the cup up this time. It's going to look like this. Increasing concave up, looks something like this. Increasing concave down, like so. All right, that is a whole lot of information, probably more than you have ever wanted to know about a graph. At this point, before we construct our graph, let's take a quick peek at the graphing calculator and make sure our information lines up with what the calculator looks like. So I'm going to go back to y equals. I'm going to clear out the old function that we were looking at in example 2 and type in our new function. Make sure you're aware here we're typing in the original function, 3x squared over, notice parentheses around the denominator, x squared plus 5. I'm going to type zoom 6 to get a good picture of the graph. Okay? Now, one thing we didn't calculate in our work were inflection points. We didn't find their y values. But because my graph goes from concave down to concave up, at this location we know there's going to be an inflection point at negative 1.29. Also because concavity changes, didn't write that one, here to here, there's going to be an inflection point here at positive 1.29. So I should be able to see the graph change concavity at positive and negative 1.29. So I'm going to type my trace button and enter negative 1.29. And notice the graph locates that point here. Okay, I want to see the change in concavity, and it's difficult in this viewing window. So what I'm going to do is press my zoom button, number 2, zoom in, and then enter. It'll just give me a closer view. Okay, so here is x equals negative 1.29. On the left side, the graph is concave down. Do you see the subtle change there? On the right side, it is concave up. Okay, and observe the y value is about 0.6. So we'll know where to plot that on our graph. Okay, now let's look at the other side. I'm going to go back to zoom 6. I'm going to locate the inflection point over there on the right side by pressing trace, positive 1.29. The cursor jumps to that point. Then I'm going to zoom in. Make sure you press enter after pressing zoom in. And then I can see the same change occurring. So on the left side of the inflection point, the graph is shaped where it's bending up. And on the right side, it's bending down or concave down. And again, it's going to be symmetric about the y-axis. Okay? So let's transfer this information to our hand-constructed graph. Remember, we discovered that the x and y intercept was at 0, 0. At approximately 1.29.6, that's where our inflection point occurs. And this occurs over here on the other side of the graph, negative 1.29 and about 0.6. So a little beyond negative 1, a little further than halfway. That's an inflection point. This is an inflection point. Okay. Also, remember, seems like half an hour ago, right? When we found the horizontal asymptote, it was y equals 3. Let's get that on our graph. So we know that's going to limit the curvature of our graph. And we're ready to sketch in our curve. Okay? So we were decreasing concave down. Then it bends up, decreasing concave up. Increasing concave up. Increasing concave down. Now that is one excellent detailed graph, much better than just a sketch. Okay, continue following these principles to work example number 4 to finish the section. And remember, 13.4 is long and detailed. Once you make it past that chapter 13 test, you are downhill for the semester. So keep studying.